Traditional authentication relies on a shared secret. A user creates a password, and a server stores either that exact password or a cryptographic hash of it. If an attacker breaches the server, they extract the secrets, exposing every account in the database. This diagram shows the structural alternative, public key infrastructure, or PKI. Here, the server no longer stores a password. Instead, it maintains a database of usernames, credential IDs, and public keys. If an attacker compromises the database on the right, they extract only public keys. A public key cannot be used to log in. It is mathematically useless without its paired private key, which never leaves the user's hardware. Passkeys are the commercial application of this concept. They are discoverable FIDO2 and WebAuthn credentials built entirely on this asymmetric cryptography. To operate securely across the internet, passkeys rely on two distinct protocols working in tandem: WebAuthn, which handles the network traffic, and CTAP, the client-to-authenticator protocol, which manages the local hardware interface. By replacing shared secrets with mathematical proof, passkeys eliminate the server as a high-value target for credential theft. The server issues a challenge, and the local device proves its identity. The passkey ecosystem requires three distinct entities to function. Looking at this FIDO2 diagram, the relying party on the right holds your public key. In the center, the client platform processor acts as the WebAuthn intermediary. On the left, the authenticator hardware generates keys. WebAuthn dictates network traffic. CTAP governs isolated local transport. The critical rule of this architecture is that private keys can never cross the CTAP boundary. They cannot enter the client's standard memory, and they cannot be transmitted over the internet. This separation of responsibilities guarantees that sensitive cryptographic signing is physically isolated from network-facing applications. The server verifies, the hardware signs. Generating a passkey for a new account requires a registration sequence known as the attestation ceremony. In this technical flow, the relying party initiates at step 3, generating a single-use challenge and its exact domain name, the RPID. At step 6, the client browser captures this payload, executing a JavaScript API call across the CTAP boundary to the authenticator. The authenticator immediately halts the process. It will not generate a key until it receives local proof of human intent. This requires local user verification. A biometric scan unlocks the hardware's secure enclave. The remote server remains entirely blind to this localized step. Once verified, the hardware generates a unique public and private key pair. Crucially, this pair is mathematically bound exclusively to the exact RPID provided in the server challenge. Returning to the diagram at step 10, the authenticator signs the challenge and routes the new public key, the credential ID, and the signature back to the web server for storage. The private key remains permanently locked inside the device's secured hardware or within an end-to-end encrypted synchronization fabric. The attestation ceremony proves that a verified, local human authorized the creation of a key pair for a specific domain. The server establishes a secure identity without ever holding a secret. When a user returns to log in, the system triggers the assertion ceremony. As shown in step 3 of the authentication flow, the relying party must issue a brand new single-use challenge to prevent replay attacks. At step 6, the browser executes an API request, pulling in the fresh challenge and the current website's RPID. The client merges the fresh server challenge and the exact domain you're visiting into a single cryptographic payload called the client data hash. The authenticator then performs context binding, cross-referencing the requested domain against its secure registry to find the corresponding private key. If the domains match and the user verifies their presence, the private key signs the client data hash to create the final accession signature. Tracing this to step 10, the client sends only this signature back to the web server. The server applies its stored public key to verify the math. The assertion ceremony mathematically proves possession of the private key for the correct domain without exposing the key to the client memory or the network. This strict hardware isolation presents a logistical problem. If a user attempts to log into a new Windows laptop using a passkey stored on an iPhone, the authenticator is physically disconnected. To bridge this gap, the protocol utilizes the FIDO2 Cross-Device Authentication Standard, or CDA. When the laptop browser displays a QR code for login, scanning it does not transmit the passkey to the computer. Sending the private key across devices would violate the strict rules of CTAP. Instead, CDA uses a hybrid architecture. A Bluetooth low-energy connection acts as a cryptographic proximity check, proving physical adjacency. Then, an encrypted HTTPS tunnel routes the server's challenge to the phone, which signs it and returns the final signature. Cross-device authentication extends the strict local hardware constraints of CTAP across different ecosystems by demanding verifiable physical proximity before executing any cryptography. How does this combination of WebAuthn and CTAP neutralize modern attack vectors? In a replay attack, a malicious vector captures a mathematically valid signature and attempts to inject it later. The server rejects it instantly because the signature is bound to an expired single-use challenge. In a phishing attack, a user is tricked into visiting a fake domain, like a misspelled version of Microsoft. The WebAuthn API captures the fake domain's RPID and passes it to the authenticator. The authenticator checks its registry, finds no private key matching the misspelled domain, and terminates the request mechanically before the user is even prompted. In this scenario, no human cognition is required to spot the fake URL. The cryptography enforces the exact boundary. By binding asymmetric cryptography to verified physical proximity and exact domain parameters, passkeys structurally eliminate the human element from credential security.